So an inner product, this generalization of a dot product that I was talking about, an inner product is a function, it's some kind of a widget that takes a pair of vectors and turns them into a scalar. So this is why it's called the scalar product, and it has to have a bunch of properties, of course. So it needs to be positive, meaning that the inner product of a vector with itself is non-negative, and it needs to be definite, meaning that 0 is the only vector for which the inner product of the vector with itself is equal to 0. And then these two are often kind of grouped together and called positive definite. So when both of those are satisfied simultaneously. And we'll talk a little bit more about why that is later on. We also require this function to be additive in the first argument. So if you have a sum in the first argument, you can split it into the sum of the two corresponding inner products worked out separately. And that it be homogeneous in the first coordinate. So if you have a scalar multiple in the first coordinate, you should be able to take that scalar and pull it out. And we require conjugate symmetry. So this means that if I flip the order, so I'm looking at VU instead of UV in the inner product, that's the same as the conjugate of the inner product with U and V. Now, quite often it'll be the case when our underlying field F is the reals, and in that case, it's just symmetric. So you just ignore the conjugate, of course, because all real numbers are their own conjugates. So let's see. So now combining the bits and pieces of this definition, we have a host of immediate consequences or conclusions. So, for instance, if we have, if we have the sum taking place in the second coordinate, we see that it's also additive over there. So this is going to be equal to inner product UV plus inner product UW. So this is like a distributivity property, sort of, right? And if you're wondering how does that work, well, the way that you prove it is you say, okay, well, this is the same thing as inner product V plus W against U conjugate by the conjugate symmetry. And so then this is going to be VU plus VW. And by the property of conjugates, we can split them over the sum. And then conjugating each of these back, we get to the other side, right? And so by some similar trick, we also have that if you have a scalar multiple in the second coordinate, then it comes out as being coming with a conjugate. So it's what we call, it's linear in the first slot and conjugate linear in the second slot. And so if we have that the underlying field is the reals, then VU is equal to UV and U lambda V is equal to lambda UV. And we say that this widget is a bilinear form. In particular, it's a bilinear form for an inner product. An inner product is a bilinear form which is positive definite. And then if F is the complex field, it's not quite bilinear, it's only 1.5 linear. And the Latin for that is sesqui for 1.5. So it's a sesquilinear form. This may or may not actually be some attempt at a math pun, but it's so bad I don't even know for sure whether or not it was intended to be funny. Anyways, moving on. So an inner product space then is a vector space that's got an inner product. So it's a vector vector product. Good God, what's going on here? Sorry. It is a vector space, Freudian slip, on which an inner product has been defined. So sometimes math hotshots like to say something like, it's a vector space equipped with an inner product. For this in chapter, and basically I guess for the rest of the book, well, let me not make grandiose claims, but definitely for chapter 6, V is going to always be an inner product. So we will always assume that there's some inner product that's been defined. And if it's Rn or Cn, then you can assume that it's the standard one, aka the dot product.